Can you hear me? Oh, whoa, that's loud. Okay, let's step back a little bit. So hello, everyone, and thanks for attending. In this talk, we're going to talk about Node in small places. That's going to mean two things: a Node running on tiny computers, and using Node and tiny computers to build more complex things. But first, a bit about me. I'm Carlos. I go by CJS on GitHub and Twitter. My first entry into the Internet of Things came in 2001 when I worked on a factory automation project using Linux-based single-board computers, or SBCs as they're commonly known. The SBCs monitored large injection molding machines for the plastics industry, and they did that over serial and TCP/IP connections. 10 years later, I learned about Node.js and soon deployed my first Node app into production for a startup here in New York, actually. These days, I'm a chief architect at Flywheel Sports, where I joined a team who's been working with IoT devices in the fitness industry for the past 6 years. So some cool things happening at Flywheel. So I've enjoyed learning about Node in small places, and I'm pleased to be able to share what I've learned with you here tonight. So I'm going to ask you to do the same by encouraging you to tweet about things you learn or find interesting during this talk. The best talk-related tweet using the hashtags NodeLovesPi and NYCNode will take home a Raspberry Pi kit this evening. Make sure to use both hashtags in your tweets because that's how we're going to search for them. So the kit we're giving away includes a Raspberry Pi, a 32 gigabyte micro SD card, and a micro USB cable. Everything the winner will need to load Node.js and begin exploring Node in small places. So here's a photo of the Pi Zero. Actually, also right here. So I'm just gonna push this out here. Just kind of pass it around, so you can just take a close look at it. So that's the Pi Zero there, and it's also, of course, a single board computer. So we're going to call these SBCs throughout the talk. Just wanted to make that clear. So as you can see, it's tiny. And you can pick up one of these for less than the cost of a lunch here in the city. SBCs are very different from computers that many of us have used. For example, they don't have a screen, keyboard, or mouse, although you can connect those if you choose. However, a really exciting and key difference with SBCs is that you get general-purpose input-output pins, commonly referred to as GPIO pins. Those pins allow it to connect to other devices such as sensors, motors, switches, and other controllers. And those things form the building blocks of robotics. So in terms of what you can do with this, really sky's the limit. Your imagination's the limit. There are a lot of SBCs to choose from. However, I chose the Raspberry Pi family of SBCs for my own personal work because they're widely used and well supported by the Node community, with lots of available Node NPM packages. That said, many of the topics we'll cover here today will likely apply to almost any SBC you choose. So here are the specs for the Pi Zero. It features a Broadcom ARM V6 processor running at 1 gigahertz. It has 512 megabyte of onboard RAM. Shown here are 2 micro USB sockets for power and data, a micro SD card slot for memory, and a mini HDMI for 1080p video. It measures only 2.5 inches by over 1 inch. So you can see why it's called a single board computer, because many of the required components sit on a single board. Best of all, it runs Linux and Node.js, and the cost is really hard to beat at only $5. Now you may have noticed that there's no mention of an Ethernet port or Wi-Fi chip in this particular SBC. The good news is that you don't strictly need this because the Pi Zero supports networking over USB. That does require you to tether the Pi Zero to a laptop. So that's kind of a little bit of the downside. But that's fine though, because especially when you're just getting started. And you can always add a Wi-Fi dongle or Ethernet adapter later if you'd like. So by comparison, the newest member of the Pi family is the Raspberry Pi 3 at just under $40. It features both built-in Ethernet and Wi-Fi, as well as Bluetooth and USB and 4 USB ports. It also has twice the memory at 1 gigabyte and a 64-bit quad-core ARM V8 processor. If you don't mind paying around $40 or under $100 as a kit, then the Pi 3 is really the best way to get started. And if you later find out that it's really not your thing, you can always use it to run a media server like Kodi or similar Linux distributions. So you can get some value even if you decide that you're kind of tired of playing with it. Let's look at what's involved in getting the lower cost Pi 0 using Linux and Node.js. But first, we need a bit more hardware. When you purchase an SBC, it doesn't usually ship with an operating system installed. You can certainly buy one with a pre-installed OS, but that's not typically how they're sold. So acquiring an SBC means that you'll need your memory card and USB cable. The good news is that you probably have spares lying around the home because they're commonly used with other consumer devices such as cameras and phones. Because most SBCs don't have an Intel-compatible CPU, you'll need to download a version of Linux that is designed to work with whichever SBC you choose. The Raspberry Pi has its own Linux distribution called Raspbian. To get a copy, we just visit the raspberrypi.org site and travel over to the download section. The latest distro is named Raspbian Jessie. Once you download and unzip the file image, you'll be able to copy it to the micro SD card. Now, I know what you're thinking, but seriously, it's not that bad. The process is actually pretty straightforward once you get into it. But if you don't want to actually deal with it, you can always go with a pre-installed copy of Raspbian, but you would be missing out on a valuable learning experience. So it's worth trying. So I'm going to give you a quick overview, because we won't have time to actually do this live on stage because it takes about 30 minutes to complete. And in truth, it's more boring than watching paint dry. I mean, literally, you do not get a response back. It doesn't move. Your machine looks hung. So it's pretty bad. But it does complete. And so first, we insert the micro SD card into the laptop. So depending on your laptop, you may need a converter, sort of an SD to micro SD or converter, or perhaps a card reader. So of course, I'm going to step through some Mac examples here, but obviously there's examples for PCs and other stuff. So on Mac, we use the disutils command to list mounted drives. The micro SD should show up on the list. In this example, the micro SD was mounted at dev disk2. Because inserting the SD automatically mounts it, for use, you need to unmount the micro SD card before using the DD command. So the third step uses the macdd command to copy a disk image, the Linux image, onto the micro SD card. So you can see there from the IF is really just the image name, and the OF is really the output file. So input file, output file, pretty straightforward. You need sudo access because you're accessing hardware. And that's it. It's not too bad, actually. 15 to 20 minutes later, you should have a micro SD card with a bootable copy of Linux on it. So this shortened URL that's shown here at the bottom provides you with detailed steps on how to do this on both the Raspberry Pi 0 and other Raspberry Pi devices. So that link is just going to appear on a couple slides, so you'll be able to see that. So now we're ready to insert the micro SD card into the Pi 0. We also need to connect the micro USB cable from the laptop to the Pi. You'll want to connect it to the centermost micro USB port because that's the one that supports data communication in addition to power. The outermost one really is just for power. So it can take up to 1.5 minutes to boot and be recognized as Raspberry Pi.local. You can ping it until it resolves, and at that point you're ready to SSH into it. You can do that by SSHing using the user name Pi and a password of Raspberry. So hey, at least the password is not password, but it's pretty straightforward. Of course, you can change it, and you should if your device is going to be networked. Now we're able to log into the Raspberry Pi, and we can make configuration changes, install applications. So one of the first applications we're likely to want to install is naturally Node.js. And as I mentioned earlier, the Pi 0 features an ARM v6 processor, which means that we'll need to download the correct precompiled version of Node. Fortunately, that's just a matter of heading over to the Node.js site on the download page. We want to right-click on the Linux binaries if you scroll down, and we want to select the v6, which is the one suitable for the Pi 0. If you're using a Pi 3, you can definitely bump it up to ARM v8. So you want to right-click on that link so that you can just copy the address, because we're going to use the address to within inside of the shell terminal. So once we're logged in, we just create a Node.js folder. We cd into it. We use a wget with the link that we just copied so that we can download a precompiled Node.js distribution right from within the actual device. So next, we'll just untar it and cd into the folder it created. And the last step is to copy the files from the current directory's bin folder to user local bin folder, which is just up. And what that basically does is it copies both the node binary as well as a symbolic link for the npm command. So it's really just copying 2 files into that folder. Again, this is a precompiled distribution, so you don't actually have to build it using build tools. So that's nice. And it's, of course, compiled for the processor that you're using. So if all went well, you should be able to cd back to the home directory and use node-version, which should show you the version of Node.js you downloaded. And it is pretty straightforward, actually. So then Bob's your uncle, the world's your oyster, and that sort of thing. So what's next? Robotics, right? Not so fast. First, you can learn a bit more about hardware by trying simple experiments. So this is the Hello World program of the SBC world. Basically, we don't have a screen hooked up, so really no way to kind of display Hello World. So the process is really to take a, to build this using a blinking LED. This is often the first thing that one does when playing with single board computers. So it's also an inexpensive project, requiring only 2 wires, a resistor, and an LED. The resistor is necessary in order to avoid burning out the LED. As you can see from the diagram, we're connecting 2 wires to GPIO pins. So now you see the GPIO pins in action. The power and the ground is what we're connecting. See, you're already learning electronics. That's a $5 investment. So let me show you some samples here. And I'm going to figure out how I can do that. I'm going to walk over, but I'm going to have to walk away from the mic. This? Wow. Wow, excellent. This is better. I should have actually done it this way from the beginning. So I'm going to kind of hold these guys up. And yeah. So basically, this is just a USB power hub. And there's a little light LED demo connected to the pins. You can see that. You can come up later and have a closer look at it. And of course, there's a sort of a fancier demo here where the Pi is actually driving a display with 55 super micro LEDs, and of course, it's just displaying a sine wave. I'm gonna put this guy down. Yeah. All right. All right. So what we're seeing here is code controlling physical devices. Let's take a closer look. Now, this code could be even easier if we only cared about turning the LED light on and off. However, it's far more interesting to fade the lights. This code does just that using the Pi Blaster NPM module on line 1. This is the node support coming in, and you'll see more of that along the way. On line 2, we specify the GPIO pin, which is pin 4, hard to see from a distance. And that's the one used to control the LED. So it's sort of pulsing in order to be able to change the value there. And so the last bit here is that we just set up a SIGINT Control-C handler so that we can turn off the LED when we exit the program. That's really what that bit is doing. So playing with single board computers is really cool. Getting them to communicate with one another is even cooler. I made that up, but I'm sticking to it, really enjoying it. So there's a lot of ways you can connect SBCs so that they can communicate with other services and with one another. From within your Pi, you can issue apt-get install to install your favorite dev apps. You can also build interesting applications which use HTTP and WebSockets and messaging servers such as RabbitMQ, ZeroMQ, and MQTT. So to play with some of these ideas, I built a 16-core cluster using Raspberry Pis. Let's have a look. it's actually moving. Okay. So friends, this is the Hydra Cluster. It consists of 8 computers, 7 of which are Raspberry Pis, and 1 of which is an Arduino microcontroller. Each of the Pis are running Hydra-enabled microservices using Node 6.5 or higher. Hydra is an NPM module for creating microservices, which we open sourced at Empire Node earlier this month. In total, the cluster contains 16 CPU cores and is running 18 microservices. Looks cool, right? I better power this on, actually. 1 second. So before we move on, I'd like to discuss this side panel showing the Hydra cluster, shown here. So at the top is a 16 by 2 LCD display, which is connected to an Arduino microcontroller. That's the computer underneath the top LCD, the one with the micro USB cable connected to it on the left side. You'll notice that the Arduino has a silver tube under it. That's a temperature sensor, which the Arduino is using to monitor the internal temperature of the cluster's enclosure. As you may know, the Arduino is far too limited to run Node, but that doesn't mean it can't perform valuable services. In its current role, it's driving the top LCD display, monitoring temperature, and sending serial data to through the USB cable to the Raspberry Pi 3, which sits at the bottom behind the green LCD display. The Pi 3 is using the Node serial NPM package to read serial data, which it in turn uses to drive the green LCD display at the bottom. So the lower display is powered by the excellent Blessed and Blessed Contrib terminal library package for Node.js. So overall, this is a real example of computers working together and communicating with one another. Here's a side view of the cluster's internals. At the bottom of the cluster is a USB power hub, which distributes power to all of the computers. Next to it is a 5-port network switch used to create a private network on which the computers can communicate. Let's have a look at this. If you're close enough to see, you'll see some activity there.
Did you use a Raspberry Pi to control the LCD instead of the Arduino?
So actually, that was a consideration because I also wanted it to control the temperature sensor. In the end, I decided that that a Raspberry Pi to be used to monitor temperature and just display on the 16 by 2 LCD was a little overkill. So decided that Arduino was far better suited for that, and also makes a very interesting point, which is the fact that Node can work with other microcontrollers, and that in the process of building and doing things, yes, we're focused on Node, but we can use these other devices to sort of complement overall what we're trying to achieve. So I thought that was a real plus to kind of keep it in. But you're right, absolutely could have driven that in more. So let me. And well, the Pi Zero, I thought so too. Yeah, the Pi Zero is actually, it was $5, but the Arduino turned out to be, I'm sorry, the Arduino was actually $6. So, okay. Because it is a microcontroller, so I mean the amount of overhead involved is considerably less than yeah, I mean it can be. I don't actually know specifically, but yeah, it could be. And again, you bring up an interesting point because you want to look at your particular problem, what the challenge is. You want to look at cost, you want to look at all the factors, and then choose from the wide variety of devices out there which one suits your project and how to kind of bring them together. For me, I'm enthusiastic about the fact that Node can function as this orchestrator of devices and other things, in certain applications. So that's of course the angle that I've approached it from. All right, let's try to connect to the cluster. Oh, cool. Okay, so as I mentioned earlier, the cluster is to a private network. What's that? Oh, gotcha. Then I can't type. Okay, so we're on a private network. There's a switch at the bottom. I'm actually connected to a cable into it. There is as you can see, a 192.168.1.10 address, and I've pointed to the Hydra MCP, which is really a program that I wrote to make communicating with the cluster. So I'll just go ahead and log in. So at the top here, we see the services that are actually running in the cluster. You can see they have names. And if I scroll down, we see these cards which actually represent each of the microservices that are running inside. So there's a bunch of them, as I mentioned earlier, 18. So actually, they're not. They're running. They're basically Node Express apps, which or using a microservice framework called Hydra. But of course, it could run as Docker containers. You could do that. And lots of people are actually looking at building Raspberry Pis and just for the purpose of being able to work with Docker containers, possibly experimentally. Okay, so if I come up here, I won't go into all of this, what this software can do, but let's look at the scheduler. Gonna need my hands here. All right, so I'm going to grab some code, and I'm going to paste it here. I guess because of the small screen size, this isn't actually formatting right, but the code is pasted inside. I'm going to go and basically change or ruin here the code, just make it change let to a bet, which isn't going to work. Now, what this software does here is it allows us to take, write JavaScript code and submit it to the cluster for processing. So I'll go ahead and first, let's try to validate this. So it comes back. Of course, it doesn't like, bet being there. So it immediately responds back. One interesting thing that it does is it shows us here the actual node, or rather process, which identified that and validated it. So we kind of get a response back from the cluster in that way. Also, we noticed, at least some of you who are on this side, that the cluster is flashing red, indicating that there's a problem. So it's going through sort of a red animated light sequence. So let's go ahead and fix the code and see what happens. We change the let, go back. So now we validate, and we're seeing green flashing lights, indicating that the code has completed. This particular code is displaying prime numbers, a classic, task for clusters, and it's just basically generating them here. So that's what this bit does. So this is an example of, microservices running and responding to stuff. Now, the way this technically works is that it is using WebSockets, it is using HTTP RESTful calls. It's got a lot going on. And again, that's powered by a tool we built, an open source called Hydra. So let's see. Let's look at another example. But first, let's see. Cool. So I just want to make a quick point, a quick Node technical point. There are 12 microservices that actually respond to distributed computing tasks. And the way that code is written is that each of those is, it's a Node, is a Node microservice that basically uses a Node V8 sandbox. So it can execute the code inside of a V8 sandbox. In case the code times out or crashes, it won't bring down the actual service, which is needed. So that's kind of an important thing to have done. So it basically allows us to execute code more safely. So what else can this thing do? So soon after this cluster was operational, I wanted to find a more complex task to use in this presentation. So what I needed was something that was going to take just a few days to code. Just didn't have a lot of time. So I got together with my buddies Rob and Ito, for some after-work brainstorming. So after some thought, we settled on a distributed search problem. What's that? Ah, not that, not that. So we thought, what if we create a large labyrinth where each compute node is placed along the edges, and they need to find a magical portal, which is the only way to escape the labyrinth. To solve the problem, each compute node would have to run the maze in parallel. You see, never underestimate the brainstorming powers that a few bottles of wine can unleash. So here's a conceptual illustration, or at least that's how it looked after a few bottles of wine. Here's actually an early draft of the map. My wife Carla tested the map and modified the initial map in order to increase complexity. The green area at the center shows where the magical transporter is located. So we assigned each of the 12 compute nodes a letter from A to L. That's going to be important in a second. And we placed each along the edges of the labyrinth. I added ruler guides to help identify locations within the labyrinth. That was useful while debugging the search algorithm. So here's the labyrinth zoomed out just to show the scale. So you folks ready to see that in action? Yeah. All right, let's do it. Oh. And I think we're getting there. Okay. All right. So I will go and grab some code. This is the maze demo. I actually should show you guys something here. So the way the cluster processes actual code submissions, right, is that you just define an ify, right, and basically it has some. We'll get to the bottom. It has some parameters that get fed into it, and ultimately what it needs to do is basically return back an object. It's the object that is then loaded into the MCP program that you saw. That's how the data is returned back. So anything you submit to it kind of follows the same structure. Okay, and as you can see from this example, actually the map is encoded at the bottom. There you can see letters for each of the nodes along the edges. And we'll go ahead and grab that code. Come in here. Let's delete that. All right. Yep, there it is. Okay. So I'm going to submit that. We'll see that it's actually processing. You can see it's going through a multicolor light display. Still thinking. And it's flashing green now, which indicates that all the nodes have completed the work. So if I scroll down, I actually see the return data, and there's a lot of it. So basically, each node returned back a map with its solution, or at least its attempted solution. So let's grab one of those and validate what actually just happened here. So if I come up, this one says it's for the character J. So this is whatever computer got assigned J is now going to, this is the response that it gave us, right? So I'm just going to grab that, and let's look at its solution. Yeah, the maze is kind of large. Sorry about that. We're getting there. Wow, okay. Hopefully I didn't pass it up. There we go. Wow, so I can copy that and let's see. Great. So I've already have one here. I'm going to get rid of that one. All right, let's take a look at this guy. Save it. So that's just some simple HTML to basically display the pre-rendered stuff. So if we come in here, oh, there it is. I thought it was empty for a second, thinking that it didn't actually do anything. So if I scroll over, I can see that J, which I think started at the end, there it is, J at the bottom there, right? So J's running around this maze trying to find, the exit. the exit actually is here. So it could not find a path to the portal exit. So let's grab some other example here. And I won't go through a lot of them. I'll show you how we can identify this. So we can see here that there's a found parameter and it's basically false. So let's just find the one that actually returns true. So let's just scroll through this. Okay, this one is returning false also. False again on E. What's that? Oh, to find it? No, that would be too easy. Have to scroll down. All right, H, no. You know why that wouldn't work? Oh, that would work. Let's try that. All right, here we are. It's funny because the reason I thought it wouldn't work is because if we search for the letter D, well, letter D appears on every map because it's on the position of the map. Of course, we should just search for true, which would not appear. Okay, I'm going to grab this. You have a tip for speeding this part up? There's a regex would probably do it. And I don't know. We're getting there. Ah, here we are. Okay. Let's grab this guy. Come back into our map. And let's just get rid of that one. Okay, so D starts at the top, and it winds its way through, going through a rather elaborate path, but it does find the exit. There. Cool. So the way this actually works is that the code that I was scrolling through, the code for the maze, actually has a parameter inside of it, which is, it just looks like a mustache or handlebars sort of tag. It gets replaced by the MCP program that's running and knows which of the 12 nodes exist, because it all can be discovered. And then that way it basically changes a letter in there and assigns it to each of the nodes. So they all receive it almost simultaneously as fast as network speeds. And then they begin sort of following the maze from that perspective. Yeah. Cool. So, we hope that, what you've seen here tonight will inspire you to explore Node in small places. If you're interested in how anything I've shown you here tonight actually works, head over to my GitHub account and view the hardware plans and the source code. So all of it is actually open sourced. I want to thank all of you for attending. If you have any questions, please feel free to reach out to me, ping me, or just ping me on Twitter. Now let's see who actually won the Raspberry Pi. Matt.
Because they were in order of humor. And the last one's the winner. And two of them are by one guy, so he's a funny guy. All right, so first runner-up, or I guess this would be second runner-up. I don't know how contests work. Anyway, one of the runners-up is, wait for it, if I can plug in the right one. I'm actually plugged into the cluster now.
That's it, man.
Come on. All right, we'll go old school. This is the suspense building. Now I'm hungry for pie. Thank goodness Turkey Day is coming. Feast incoming. Double hashtag. The second one is Today I learned small computers can have some big cases. I don't know if you guys saw the giant case that this thing rolled into, so that gave me a good chuckle. And the third one, which is inspiring as well, is my dad, an electric engineer, said, never become a programmer. I did, though, and now I can program electronics. Take that, Pops. So Brooks Stevens, you win a Raspberry Pi.
So who was that?
Where's Brooks? Brooks, boom, there he is. Cool.
All right, man.
All right, congrats. All right, I'll hand back over here, and we will open up the floor to Carlos one more time for questions. Does anybody have questions for Carlos?
So how much did it cost? How much does this baby cost to build?
The Raspberry Pi, there are 4 of them. Actually cost $5 each. So there's that. It has 3 Raspberry Pi 3s. So those are $40 a piece. So overall, all said and done, it's pretty expensive piece of equipment. And when you count the switch, power hub, and the case is probably the most expensive piece because it was laser etched in a shop in Brooklyn, from like Illustrator plans, right? So that was kind of an expensive thing. The first case we built had really rough edges, cut plexiglass, and just felt like, hey, it's worth getting a nicer case. So.
Clustering with Pi zeros.
Oh, that's a great question, actually, and that is a great question. So there is a product called the Cluster Hat, which is made in the UK. So basically ordered that guy, and it has software which basically uses the USB, data USB on each of the Pis and creates a network bridge. It's actually really interesting because what I learned from it was, sort of how these software bridges work. It's just kind of some interesting network leveling up as a result of trying to get those guys up and running.
What's the maximum amount of nodes you can have on a cluster hat?
So the cluster hat itself only allows 4. So you'd end up having to power those. Now, I mean, many of you have probably seen other plans for larger ones, right? I saw one that had, I don't know, lots and lots of them.
Can you serially connect cluster hats?
So no, as far as I know, you can't. And it seems like each one has to be connected to an actual, Raspberry Pi 2 or 3. Yeah, definitely looking forward to seeing, larger sort of cluster hat iterations. It turns out also, as a follow-on question some of you might have, is that, so how fast is that networking over USB? I mean, it turns out because the distance is so short, it actually is pretty fast. I don't have the exact number, but it's very fast because it happens to be so close in terms of how fast that, how short the data is traveling. So.
Any last questions?
I have a small question.
Yeah.
I just want to confirm what you said. I think just take a small Wi-Fi dongle and plug it into a Raspberry Pi Zero, just like the older Raspberry Pis, correct?
Yeah, and in fact, there is a device which unfortunately is 3 times the price of the $5 Raspberry Pi on Amazon. But it's a device that allows you to connect an Ethernet. It's a USB hub, so you can attach your keyboard, mouse, and maybe a storage unit, and turn this into like this little thing that you can actually work on Linux-related stuff, which is pretty neat overall. I mean, just in terms of cost, but it absolutely works. Yeah.
Was it like an AI? Was it actually searching for the center, or was it just looking for all available paths and it happened to find the center?
No, the algorithm is really, unfortunately, not something I'm proud of, but the code is posted. It is pretty dumb. And what it does is it's traveling paths. It's looking around. It's actually looking to see which path is open, which meaning it's not going to go through walls, and also looking at which path it hasn't been to or has been to least. So it gives it the ability to do some backtracking when it's gone down the wrong way. It can work its way back around just based on keeping track of where it's been. Yeah, there were some challenges with it, but it worked well enough that I thought, okay, we're going to go with this. Otherwise, it's not going to be a demo. So.
Any last questions? All right.
Oh, thanks, everyone.